Greetings and salutations, magical chemists. Today we finally get to talk about chemical kinetics, which is the part of chemistry concerned with the rate of chemical reactions, or how fast they go. In our previous unit, we talked a lot about whether or not a reaction is spontaneous or thermodynamically favorable, but that says nothing about how fast it's going to go. Spontaneous does not mean fast. A reaction can be spontaneous and be super slow as well. So thermodynamics answers the question of if a reaction will proceed. Kinetics, however, answers two questions: how and how fast. Well, if we're going to talk about how fast a reaction runs, we need to talk about the rate of a chemical reaction, which is just literally a measure of how fast the reaction occurs. When you're looking at reaction rate, it's defined as the change in concentration of a reactant or a product per unit time. It could be per second, it could be per minute, it could be per day. It depends on the reaction. Now, the units of rate are always going to be the same. It's going to be molarity, because we're looking at change in concentration divided by time. You can write that in different ways. This could be molarity times time to the -1. Or, remember, molarity is just moles per liter. So it's moles divided by liter times time, which is the same as saying moles times liter to the -1 time to the -1. But all of those units are the exact same thing. Now, you may have noticed when you're looking at the rate up above, when they're talking about the change in reactant, they gave it a negative sign. This is because, of course, as a reaction proceeds in the forward direction, the reactant concentrations are going to decrease. So the change in concentration of reactants is negative, so the negative sign in front of the change of the reactants makes the overall rate positive. Sometimes they'll just talk about the rate of reactant consumption, which also makes the rate a positive change. Now, it is important to recognize that as time goes on, the rate of a reaction is just generally going to slow down because you're using up the reactants. Or more officially, the concentration of the reactants decreases. Now, at some point, the reaction is going to stop. This could be because you've reached equilibrium, or this could be because you ran out of reactants. Eventually, every reaction is going to stop someday. It should not surprise you to know that stoichiometry, or the coefficients of the balanced equation, have an effect on reaction rate. Mostly because you're going to be using something up. Remember how it's basically like when we were converting to moles of a reaction. If there are 3 moles of something in the balanced reaction, you're going to use that up 3 times as fast as you would something if there's only 1 mole of it in the balanced reaction. So what we do to make sure that we're consistent for the change in concentration of the overall reaction, we basically take the change in concentration of each substance and we multiply it times 1, divide it by its coefficient from the balanced reaction. So for instance, given a generic reaction, A plus 3B produces 2C, notice if you wanted to get the rate of the reaction, it would just be negative the change in the concentration of A divided by the change in time, because of course the stoichiometric coefficient of A is 1. But if you were doing this for B, it would be 1/3 times the change in B divided by time, and of course still negative because it's a reactant. If it was C, it would be 1/2 times the change in concentration of C divided by time. No negative needed, because this is a positive change because you're making products. Okay, so let's go ahead and try a quick example. It'll be delicious. So we have a reaction given. 2 nitrogen dioxide molecules are going to decompose, producing 1 molecule of oxygen gas and 2 nitrogen monoxide gas particles. And we know through experimentation the rate of production of nitrogen monoxide is 8.57 times 10 to the -6th, and then of course rate is always going to be in units of molarity per time, in this case molarity per second. So we want to know, okay, well that's the rate of production of nitrogen monoxide. What's the rate of NO2 consumption? All right, so go ahead and pause the video, take your best guess, and when you are ready to check your answer, unpause the video. Okay. Did you notice something sneaky here? If you were looking at the stoichiometric coefficient of NO and NO2, they are the same. This means that the rate that NO is being produced is exactly the same rate that the NO2 is being consumed. And because of the language they're using, they're talking about consumption and production, we don't even need to worry about throwing a negative sign in there because the negative is implied by saying it's being consumed. All right, what about the rate of O2 production? If you haven't tried this yet, go ahead and pause the video, and then when you are ready to check your answer, unpause the video. Well, if you were looking at the stoichiometric coefficients here, you would notice it is a 1-to-2 ratio, right? Because basically, oxygen doesn't have a coefficient, which means it's implied to be 1, but NO has a coefficient of 2. Which means for all the NO being produced, half of that amount of O2 will be produced. So basically, this is half the rate. So we just need to take the given rate and divide it in half. And so mathematically, once you do that, you're keeping, of course, the 3 sig figs that you started with. You get 4.29 times 10 to the negative 6th. And this, of course, is molarity per second. And you're done. Short and sweet. All right, let's move to the next page, and we can talk about the factors that affect your reaction rate. We are going to come back to these throughout the course of our kinetics unit, but these are super important. They will show up all the time, and OMG, they are so worth memorizing. So there are 4 specific factors that you need to know. You may remember some of these from pre-AP. First, if you increase the surface area of a solid reactant, well, you're increasing the rate of the reaction because you're increasing the number of collisions between reactant particles. This is the classic where if you have a cube of sugar, and then if you grind it up, it's going to dissolve a lot faster than if you just let the cube sit and dissolve. You also can increase the rate of reaction by adding a catalyst. Catalysts are basically defined as something that increases the rate of a reaction. The way they do this is by offering an alternate pathway, which will lower, whoops, that's not a highlighter, which will lower the activation energy of a reaction. So we're going to talk a lot more about that later, but for now I just wanted to throw that word out there. Yes, catalysts will increase the rate. All right, we also have the third thing that you can do is increasing the temperature. Remember, applying heat, that is going to be increasing the kinetic energy. So if you heat them up, you speed them up. The rate constant, which we'll talk about shortly, is temperature dependent. So automatically, increasing the temperature increases the rate constant. All right, last but not least, if you increase the concentration of reactants, well, now there's more reactants colliding with each other, so you get more products. So that's another way to increase the rate. Okay, now that you have a just general understanding of ways we can increase the reaction rate, let's look at what's known as the rate law more specifically. So the rate law is a mathematical expression that relates the rate of the reaction to the concentrations of the reactants. Now, it is essential to note that the rate law must be determined experimentally. You've got to do something in lab if you want to know the rate law. The generic form of a rate law is always going to be the rate equal to K, which is the rate constant, multiplied times the concentration of each reactant. So we've got a generic reaction up here, right? So the concentration of A raised to the nth power, the concentration of B raised to the mth power. That's not awkward at all. So these exponents, the things you are raising them to the power of, these are called the order with respect to that reactant. It's important to note that N and M, notice they're not the stoichiometric coefficients, at least not necessarily. Sometimes they will, sometimes they won't. The only way you can tell is through experiment. Now, as you can probably tell from the way that this equation is arranged, if you increase K, the rate goes up. It's a direct relationship. So a larger K means a faster reaction. You can also add those exponents, N and M, and you get something that's occasionally referred to as the letter P, which is the overall rate order, which is just the order of the entire reaction. Okay, now something else that's important to note. The concentration of the products are not appearing in the rate law, because when we are studying the reaction rate, we're studying it under conditions where the reverse reaction is not contributing to the rate, which means you're usually measuring it while you're starting with all reactants. So you will never have products in your rate law, only reactants. Okay, so let's go ahead and take a look at an example. So here is a specific reaction and its rate law. Notice it is the experimentally determined rate law. So if you were describing this rate law, we would say, well, they want to know what's the order of the reaction with respect to nitrogen monoxide. Well, that means we just need to look at the exponent. Well, it's to the second power, which means it is second order with respect to nitrogen monoxide. They also want to know the order with respect to oxygen gas. Well, that doesn't have an exponent, which just means it's implied to be 1, right? Chemists, mathematicians, we're too lazy to write the number 1 when we don't have to. But that means it is first order with respect to oxygen gas. Thus, it is third order overall, of course, because 1 plus 2 is 3. All right, so now let's go ahead and try an example on your own, just because we can. So you're given an equation and you are given this experimentally determined rate law. So I want you to figure out the order of the reaction relative to nitrogen dioxide, relative to F2, and the overall reaction order. When you are ready to check your answer, pretty please unpause the video, which I guess means first pause the video, try it, and then unpause the video. All right, how'd you do? Hopefully this is pretty straightforward. So guess what? You're done with this video. On the next video, you're going to go ahead and learn how to take experimental data and derive the rate law using that. Thank you for playing. I'll see you in the next video.